Psychoacoustics. It's Dr. Gilchrist, and we are back to talk about hearing. Now, the last time that we were here, we were talking about the different ways that we can code for frequency. So we talked about place coding in the cochlea, and that place coding is maintained in the auditory nerve. We also talked about using time coding, so temporal coding, because certain neurons phase lock on a particular frequency, but this would severely limit the types of sounds that we can hear. So this would really only work up to a certain amount of hertz. So what we talked about last time is that neurons can fire in different parts of a cycle in the auditory nerve, and these neurons can basically add up and summate that time locking to basically have a firing rate that matches the frequency. So we basically have that firing in a volley. So let's talk about some of the different areas that basically once the auditory nerve actually leaves the ear, what are the areas that of the brain that make contact? So the first area, when the auditory nerve fibers basically leave the ear, the first place they make contact with is the cochlear nucleus. From there, they make contact with the superior olive. So here's something that's really kind of important to know about hearing. When we talked about the visual system, basically we had information from one eye or one part of the visual field going to one hemisphere, information from the other visual field going to the other hemisphere. Now, what's really interesting to me, and we'll talk about this more next chapter when we talk about hearing in the environment, you need to be able to notice time differences and intensity differences to be able to localize where a sound is. And so one of the things that's actually kind of interesting is that by and large, information from both ears is present in both hemispheres of the auditory system in the brain, starting at the superior olive. This is where inputs from both ears converge, allowing us to be able to account for those timing differences or those intensity differences. So unlike a lot of the other sensory systems, we get information from both ears in both hemispheres of the brain. From the superior olive, information goes to the inferior colliculus, which also is critical for localizing sound, and then the medial geniculate nucleus of the thalamus before making final contact with the primary auditory cortex. So here's how this kind of works. So here we have our auditory nerve fiber basically leaving the cochlea, making contact with the cochlear nuclei. Both ears are basically providing converging input at the superior olive at that point. So we need information from both ears at this point. Then we have our inferior colliculus, the medial geniculate nucleus of the thalamus, and then finally the primary auditory cortex. So what are some additional brain structures that we have that are critical for processing sound? So we have our primary auditory cortex. You can kind of see it right here. Most of it is buried under the sylvian fissure, so most of it is not visible from the outside of the cortex. This is the first area in the temporal lobes that actually processes sound. And like the cochlea, and the auditory nerve, it does have a tonotopic map. So information in the primary auditory cortex is organized by frequency. We have this area here coded in yellow. This is called the belt area. And then just below that, we have what is called the parabelt area. Now, as I mentioned, the entire auditory pathway is tonotopically organized. So neurons are organized anatomically in order of frequency. So that starts in the cochlea and it's maintained all the way up to A1, primary auditory cortex. Now, you could draw the analogy that just as the visual system is retinotopically organized, and that retinotopic map is basically maintained through the entire visual pathway, the same is true for the auditory pathway. That tonotopic map is basically maintained. But here's what's kind of interesting. In the visual system, the majority of processing does not begin until primary auditory cortex and extrastriate cortex. In contrast to the visual system, the most of the auditory processing occurs before primary auditory cortex. So now we're going to talk a little bit about how the auditory system operates. And if you want to know how that operates, you can look at work from Psychoacoustics. This is a branch of psychophysics that studies the psychological correlates and the perception of auditory stimuli. So one of the things that's kind of interesting is that intensity and loudness often interact with each other and actually change how we process a sound or how we think of a sound. So one of the ways that we can actually kind of see this in action, you know, I'm a big fan of the companion site. So let's go ahead and we're going to try something. So what you're looking at here are different types of tones, and I would encourage you to try this on your own, possibly with headphones. I tried this yesterday with my computer sound, and I don't think it worked as well as it could have. So here's what we're going to do. We're going to start with our 1000 hertz tone. So I can hear that pretty well. Now, what you're supposed to do in this particular case is just play that. And then let's see. So you can hear that. Now I'm going to click the 100 hertz. Actually, let me click on, I don't think I can. All right. So now I'm going to play this one. And it's kind of hard to hear, right? That's a 100 hertz tone. So I'm going to have to make it a little bit louder. Okay, I can hear it probably about here. So what you want to do, these little arrows can help you adjust the volume of the sound so that you can actually just audibly hear a certain frequency. Now here we're going to go to 4000 hertz. Okay, that's pretty noticeable. So now what I'm going to do, I'm going to see if I can modify that till it's just barely noticeable. So in this case, the sound doesn't need to be as loud at that frequency for you to hear it. It's pretty audible. Here's 8000 hertz. Yeesh. Yeah. Okay. So what you're basically trying to do here is you're trying to construct what we call an audibility curve. So your perception of a sound at a particular frequency also partially depends on the frequency of the sound, and it also depends on the loudness of the sound. And so what I'm going to do is show the audibility curve. And I think 8000 is a little bit of a fluke. I don't think it needed to be this loud. See, hear that? That is too loud. But what we tend to find, this is what we call an audibility threshold curve. So basically, sounds on this curve, we perceive them as being equally audible. So for us to hear low frequencies, they need to be really loud. For higher frequencies, they don't need to be as loud. Now here's what's especially interesting. We're going to perceive these sounds as being equally loud. So let's try that with 100 hertz. Okay, there we go. So I'm having that sit right on that curve. So I'm going to play my 1000 hertz. Yeah. 100 hertz, like I said, this might work better with headphones. But what's interesting is that along this line, these sounds should be perceived as equally loud because our perception of the sound depends on its frequency as well as its amplitude. So this is a fun little thing that you can try. So an audibility threshold is basically a mapping of just barely audible tones of varying frequencies. And then above that, we can create what are called equal loudness curves. So we basically plot the sound pressure levels in decibels against frequency. Anything that falls on that line is going to have equal loudness, despite the fact that they might be perceived at the same even though they're being presented at the actual same intensity. So if we have, so for example, here we've got a 0.2 kilohertz tone presented at 70 hertz. And here we have a like a 0.8 kilohertz tone that's being presented at 60. Now these are both falling on this equal loudness curve, which means that we will perceive that their loudness is the same, despite the fact that this one's being presented at 70 and this one's being presented at 60. They'll both be perceived as being 60 decibels. Now, on the other hand, here we have a tone of about 0.1 kilohertz at 40 decibels. Here we have one of 2 kilohertz at 40 decibels. And what's interesting is despite the fact that they are being presented at the same loudness, because of the interplay of frequency and intensity, we actually perceive them as being different. So this is a case where frequency of a sound helps you with your perception of a loudness sound. And what's really critical is that the perceived loudness may not actually match up with the actual loudness. And that's kind of weird and very cool. In addition, duration will affect how we perceive a sound. And this is because of what is known as temporal integration. If I present a sound at a constant level, it is perceived as being louder when it is at a longer duration. So if you're presenting like the tone that I presented the other day that was 2000 hertz, and I presented that for a longer period of time, you'll perceive that sound as being louder than if I had that same tone and only showed it for a second. And it turns out that there's an analog for this with brightness in vision. If I present you with a bright light for a longer period of time, you're going to perceive that as being brighter than if I presented that same light but for a shorter period of time. So in addition to frequency affecting how we perceive sound, duration does as well. And we can also talk about how we examine frequency perception. And generally, human beings are really, really good at detecting changes in tones. So one of the ways that we can kind of test this, I'm going to pull out my tone app on my phone again and play a tone of 500 hertz. Okay. So hopefully you got that. Now I am going to play another tone, and I need you to tell me if this is the same as the tone I played or if it's different. Hopefully you noticed that there was a difference. The first tone was 500 hertz. The next tone was 515 hertz. So we're really good at noticing differences in tones. So that's one thing that we know. We're very sensitive to frequency changes. In addition, researchers have looked at studies of how selective we are for frequencies. So what we can do is we can look at what is called a critical bandwidth. So basically what we do is we use masks to make detection of a sound difficult. And typically we're going to use something like white noise. It kind of sounds like television static, like or something like that. And we can look at what's called a critical bandwidth, the range of frequencies that you can listen to within an auditory channel. So here's how it kind of works. So what we do is we embed a tone and we basically mask that tone with noise. And what we're going to do is we're basically going to widen the frequency of that white noise. So we're going to start with the tone embedded here at 2000 hertz. So we're basically masking the noise and we're figuring out if people can detect the tone. Now the tone's going to be really hard to detect, but generally people can do it pretty well. One of the things that we'll find is that up to a point as you widen the frequency of the noise that this is embedded in, it will be very difficult to detect the tone. So you'll kind of notice here, so here we've got the masking noise bandwidth for a particular tone. And what you can see is that as we increase the amount of noise, as we widen the noise, detection gets very difficult to do, but people can still do it. Now, at some point, the point that we call the critical bandwidth, at this point, no matter how much we widen it, detection basically levels off and the amount of noise no longer makes a difference. So this also kind of shows how we can select and attend to different frequencies as they're buried in noise. So what does this tell us? Well, the first thing that it does tell us when researchers do this is that the width of the critical bandwidth actually depends on the frequency of the test tone. And generally, we tend to find that the critical bandwidth is much smaller for low frequencies than it is for higher ones. It's a lot easier for us to detect high frequencies in noise than it is for low frequencies. And that's just because, in general, lower frequencies are harder to hear. So now let's finish up by talking a little bit about hearing loss. So I want to talk about the difference between hearing loss versus deafness. So when we're talking about hearing loss, we're talking about the threshold for being able to detect a sound as being changed. In particular, we're elevating the threshold for sound detection. And that basically means that it gets harder and harder for us to hear a sound. So when we elevate a threshold, it means it's going to be harder to detect. Generally, deafness is going to be more difficult to acquire. Hearing loss, on the other hand, can occur through a variety of ways. Now, I will mention that even though I'm talking about this in terms of a threshold and detection, it's not just confined to that detection. It may also involve difficulties with interpreting sounds or noticing differences between frequencies or noticing different words that people are actually saying. So why does hearing loss happen? Hearing loss will happen if you damage any part of the auditory pathway. This can occur through a variety of different ways. It can occur through obstruction to the ear canal. If you use earplugs too much, that can lead to hearing loss, albeit a temporary one. So we know that if you use an earplug, it basically blocks the ear canal. It cuts back on some of that filtering. And thankfully, that's temporary. You just remove the earplug and you're done. Don't get an earplug stuck in there. You can also have obstruction to the ear canal that will affect hearing loss if you have too much earwax buildup. In addition, you can have conductive hearing loss. This is a case where you actually have issues with the ossicles themselves, such as with something like this. This is otosclerosis. So basically, you can kind of see that normally the stapes is very, very smooth, so it can attach to the membrane of the oval window. Here, with otosclerosis, we can see that there's kind of a bumpy buildup, and because it can't perfectly attach to that oval window at that point, amplification is going to basically be damaged. Conductive hearing loss can also happen with things like ear infections here and otitis media, which is another type of ear infection. Now, the most common form of hearing loss, though, is what we call sensory neural hearing loss. And this occurs because of defects or damage to the cochlea or the auditory nerve, as well as injury to the hair cells. So for example, certain types of antibiotics or certain types of cancer drugs are what are known as ototoxic. So certain types of drugs will actually permanently damage the hair cells. Remember that these are specialized neurons that cannot regenerate. So if you damage them, they're pretty much done. But generally, the most common form of sensory neural hearing loss is due to prolonged exposure to noise. One of the things that we find is that the more The more that you expose yourself to loud noises, the hair cells will twist more, they'll shift more, they may potentially become permanently damaged because of excessive shearing and tearing. And we do know that the older that you get, the greater your exposure to noise. So as you age, hearing loss becomes more and more likely. That's especially true for higher frequency sounds. And that's because higher frequency sounds tend to be preferentially coded at the base of the cochlea, at the very opening of the cochlea. So if you have a really loud sound and it enters the cochlea, that intense wave is going to primarily affect the base more than it will the apex. And as such, one of the things that we see as we age is that higher frequency sounds and being able to hear them becomes damaged. So here are some of the different effects of noise and age. What you're looking at here are people who are, so what you're looking at here is data from people who lived on Easter Island. It's generally very quiet there. Versus people who eventually spent some time away and went to noisier places in the outside world. So what you can kind of see is that for the people who stay on the quiet island, generally their hearing loss you do see some drop off with frequency, but certainly the more exposure to noise that you get, the greater your hearing loss becomes. Here on the right, you're looking at the effects of age. So right here, we're looking at age groups 45 to 54. There's not a lot of drop off there. By the time that we get to over 65, those higher frequencies are significantly more likely to be lost. And because of that, you will often see things like hearing aids being prescribed for those situations. One thing that I will mention, because y'all are young and I know I use headphones and you use headphones as well. One of the things you have to watch out for when you wear headphones is they are getting direct input into your ear canal in a way that outside loud noises really don't. So generally, they have the potential to cause more damage, especially if they're going directly into your ear. It's been suggested that you wear over-the-ear headphones if you can. If you'd prefer not to, what I would say is try to avoid using them when possible. Play them for no more than 60 minutes a day, no more than 60% of volume. And generally, part of the reason that headphones can be so dangerous, like I said, they go shooting right into your ear, especially if you're using an earbud, right into that ear canal against the eardrum with no degradation of any kind. And especially if you're in a noisy environment, you are going to turn those headphones up and as a result cause further damage. Now, hearing aids can be developed and are used for people with sensory neural hearing loss. Some of the earliest methods actually involved horns like these, but generally what we use now are amplification systems that increase sound pressure levels. Now, older ones tended to have the problem that they would amplify everything, not just they would amplify everything. So not only would they amplify what you wanted to hear, they'd amplify the noise as well. More sophisticated hearing aids, what we're kind of seeing is the following. So because we're increasing the intensity of noises so that we can hear, we basically have all of these different things that are being compressed to basically have this smaller range of intensity. So what we're often going to find is that very, very pleasant sounds for people without this damage are going to have a much harder time processing this. So they're going to compress all of these different sound intensities, so there's a smaller range that we can hear. Now, cochlear implants are different. These are used to provide hearing to previously deaf people. Generally, there is the implant, which you can kind of see in this image, is implanted as closely as possible into the apex of the cochlea. It's basically an array of electrodes that are designed to function as input to the auditory nerve and basically function as hair cells. This implant will basically be connected to a receiver that is inserted beneath the scalp. It's connected to a microphone and a transmitter. The electrodes become activated when sound signals are picked up, and they stimulate auditory nerve fibers. Now, what's really critical for this, you have to have a working auditory nerve to be able to use a cochlear implant. If you do not have a good, healthy auditory nerve, a cochlear implant cannot be used. All right, folks, so that is all I had, and I will see you next week to talk to you about hearing in the environment. See you then.